So let's understand geometric series a little bit better. We saw it in our last video. The geometric series is the statement that 1 over 1 minus x is equal to its Taylor series, this thing, when x is in between -1 and 1. So the name for this is the geometric series. It's a special case of a Taylor series for the function 1 over 1 minus x at x equals 0. So for instance, if I plug in x equals 1/2, 1/2 is in between -1 and 1, I get 1 over 1 minus 1/2 is equal to 1 plus 1/2 plus 1/2 squared plus 1/2 cubed, and so on. This, if you simplify, is equal to 2. So that says this infinite sum, adding an infinite number of terms, is equal to 2. That's an example of something known as Zenos Paradox, possibly. Let's pretend I have a length of 2 miles. So I have a straight road, 2 miles. So here's mile marker 0, mile marker 1, mile marker 2. And I'm physically going to run the 2 miles from starting at 0 and going to 2. Well, if you're going to run 2 miles, you first have to run 1 mile. So if I'm starting here and I'm running all the way to 2, I first have to pass the 1 mile marker. So I have to run 1 mile before I can run 2 miles. Then, if I'm here at mile marker 1, in order to get to the end, I next need to pass the halfway point. So there's a halfway point in between 1 and 2. The distance here would be 1/2. And in order to get to 2, I first have to pass this mile marker here. Then once I'm at this position, I still need to get halfway to 2 before I get to 2. So here's a halfway point. I'm splitting 1/2 in half, so I have 1/2 squared. In order to travel to 2, I first have to pass this value as well. And I could repeat this idea. No matter where I am, I have to go halfway to my destination before I get to my destination. So this next distance here would be 1/2 cubed, and so on. Half, 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 I get an infinite number of locations I have to pass before I get to the end. So this is like kind of a description showing why 2 is equal to 1 plus a distance of 1/2 plus a distance of 1/2 squared, and so on. I have to go all of these infinite number of distances to travel a length of 2. So that's kind of an interpretation of what this equation might mean in the case when I have 2. All right, let's do another example. Let's simplify the sum, n going from 0 to infinity, of -1/2 to the n. This is a nice and simple problem. It's exactly the geometric series, except I'm plugging in x equals 1/2. And here I guess I chose to write the sum index with k. Here n, that doesn't really make a difference. It's still the same sum. So the answer is 1 over 1 minus -1/2. And so that's the answer. This is some number. Let's do another example. What if I have the sum n going from 2 to infinity of 1/4 to the n? So this is again almost a geometric series, except this time my sum starts at 2. So this is 1/4 squared plus 1/4 to the third, and so on. I can't instantly use this formula for a geometric series because this has the sum starting at k equals 0. The power of x to the 0 is the first term. So in order to adjust for that, there's a couple things you could do, but what I like to do is I like to add in the terms that I'm missing. So I'm going to add in 1 plus 1/4 to the first power plus 1/4 squared plus 1/4 to the third, and so on. So I added in these first two terms that weren't there originally, so I have to subtract them off later. So minus 1, minus 1/4. And now this sum in here is a geometric series, so I can use this equation as stated. So I get 1 over 1 minus 1/4 from the parentheses, and then I still have minus 1 minus 1/4. So there I get a number, an actual number as this sum. Let's do another example. What if I have this sum starting at 500 of 5/4 to the n? Well, I'm missing the first 500 terms. Like in this last problem, I was missing the first two terms. I can add those in and subtract them again later, but I notice that this time the value 5/4 is outside of the range. It's outside of the interval from -1 to 1. So that means this does not give me a nice finite number as an answer. It's like adding, so 5/4 is, what is that, 1.25? So I'm adding an infinite number of numbers bigger than 1 together. It does not give me a sensible answer. So I'll just give nonsense. As we'll see in a future video, the term for this situation is a divergent series, but I'll define that in the next video. So this is a divergent series. Let's do one final example of a geometric series. What if I had the sum n going from 0 to infinity of 6 to the n plus 1 power divided by 7 to the n plus 2 power? Well, I'd like to use my geometric series idea, but it doesn't look exactly like I need it to yet, so I'll fix it a little bit. I'll factor out a 6 and a 7 as 7 squared. So watch this. I can write this as 6 to the first times 6 to the n over 7 squared times 7 to the n using properties of exponents. This sigma notation stands for addition. So I could factor terms out of addition. This is the same as 6 over 7 squared, the sum going from 0 to infinity of 6/7 to the n, factoring out this constant term in front. Now I can use a geometric series with x equals 6/7. So the final answer is 6 over 7 squared, 1 over 1 minus 6/7. All right, excellent. See you next time.